And we're back. So, let's remember what this previous video said. The preceding video says that if you have a closed bounded interval and a continuous function on that closed bounded interval, then that continuous function is actually uniformly continuous on that closed bounded interval. And like most of the properties that hold for closed bounded intervals, it's probably true for compact sets. And somehow you'll notice the proof that we did is, well, we constructed some sequences. We found convergent subsequences of those sequences whose limits were in the interval AB, and then we used continuity from there. Well, this trick about sequences, that's exactly what we know about compact sets. So in fact, it's true that the following is true. Let K be a compact set, and f be a continuous function defined on K, then f is uniformly continuous, and maybe just for emphasis, on K. Right, the function itself is only defined on K, so saying it's continuous just means it's continuous on its whole domain. So let's do the proof. The proof will be almost the exact same as what we just did, so I'll go through it pretty quickly. Suppose for the sake of contradiction that f is not uniformly continuous, then what do we know? We know that there exists a single epsilon greater than 0, right? So this is just by negating the definition of uniform continuity, such that for every delta greater than 0, there exists some pair x and p in K, such that absolute value of x minus p is less than delta, so x and p are really close to each other, but absolute value of f of x and f of p is greater than or equal to epsilon. So there's a bunch of inputs which get close to each other, for which the corresponding outputs don't get close. And instead of thinking about this for absolutely every delta bigger than 0, we'll just get a sequence worth of deltas. So let's do that. So let's construct a sequence out of that fact. Let's take the epsilon above. Right? Epsilon is just some number. I don't know what it is, but it doesn't depend on anything. It just exists some epsilon. I guess it depends on what the function f is. Let's let delta n be 1 over n, just like before. By the failure of uniform continuity, which is the line above, we see that there is a sequence worth of inputs p sub n and x sub n, which are in K for every n, such that absolute value of x sub n minus p sub n is less than delta sub n, and absolute value of f of x sub n minus f of p sub n is greater than or equal to epsilon. Now, I have this reformulation of compactness, which I called sequential compactness in the lecture about compact sets. Since the set K is compact, I'll use this sequential reformulation to see that there exists a subsequence x sub n sub k of x sub n, which converges to an element of K. Alright, so let's let x sub n sub k be that convergent sequence. Let's let x be the limit of that convergent sequence. It happens to be in K. Now, let's think about the difference between x sub n and p sub n. The notes that you should have this typo corrected. Alright, well, x sub n minus p sub n is less than delta, which goes to 0. So, by the squeeze theorem, if you like, x sub n minus p sub n converges to 0. Well, since subsequences of convergent sequences converge to that same limit, x sub n sub k minus p sub n sub k converges to 0. So, since x sub n sub k converges to x, and x sub n sub k minus p sub n sub k converges to 0, it follows that p sub n sub k must also converge to x. Right, so that should seem almost the same as what we did before. Maybe the jobs of x and y are switched, but it's essentially the same proof. Now this element x is in K, and by assumption, this function f is continuous on the set K. That means this function f is continuous in particular at x. Well, let's just think about this x sub n sub k and a sub n sub k now. So not a sub n sub k, p sub n sub k. Since x sub n sub k converges to x, and f is continuous at x, f of x sub n sub k must converge to f of x. Since p sub n sub k converges to x, and f is continuous at x, f of p sub n sub k converges to f of x. So it must be that the limit, as k goes to infinity, of f of x sub n sub k minus f of p sub n sub k is 0. Right? Two things which converge to the same limit, their difference will converge to 0. Great, well now we'll get basically the exact same contradiction as before. F of x sub n sub k, f of x sub n minus f of p sub n is greater than or equal to epsilon for every n. So it follows that for every k, f of x sub n sub k minus f of p sub n sub k is greater than or equal to epsilon, so that the limit, which, well, we know it exists, we know it's equal to 0, so that limit must be greater than or equal to epsilon, which in turn is greater than 0. So that's a contradiction, because this means that the limit of f of x sub n sub k minus f of p sub n sub k is greater than 0, but the limit of f of x sub n sub k minus f of p sub n sub k is equal to 0. There's a contradiction, so this function f must be uniformly continuous. Well, great. I hope those of you who watched this video enjoyed it. I'm going to close with doing some exploration about what do you know once you know a function is uniformly continuous. And maybe I'll state the theorems right now, and we'll come back and prove them in the next video, or maybe the next 2 videos, depending on how timing works out. Uniformly continuous functions preserve bounded sets. If U is a bounded set, and f is uniformly continuous on U, then f of u is bounded. And notice that's absolutely different from the behavior we've seen about continuous functions. If you take f of x equal to 1 over x, and u equal to 0, 1, then f of u is 1 to infinity, is not bounded. So continuous functions need not preserve boundedness of sets. Let's let u be a subset of R, and f from u to R be a function. If f happens to be uniformly continuous on u, then for every Cauchy sequence of elements of u, f of x sub n is also Cauchy. So what is this saying? This is saying uniformly continuous functions preserve Cauchy sequences. And that's also not true for an arbitrary continuous function. Let's stick with considering f of x equal to 1 over x. Well, here's a sequence. X sub n equal to 1 over n is convergent, and so is Cauchy. But f of x sub n will be 1 over n is not Cauchy. So a continuous function might take a Cauchy sequence and turn it into a non-Cauchy sequence. And the last one to mention is the following. Let's let u be a subset of R, and f from R, u to R be a function. Again, those typos will be corrected in the version of the PDF that you'll find online. Let's let P be a limit point of that domain U. Then the limit as x approaches P of f of x exists. So what this says is if you have a uniformly continuous function and you see a place where you want to take the limit of that function, you can. And let's see if that holds for continuous functions. And instead of using 1 over x again, I don't know. How about this? Let's take f of x equal to the sine of 1 over x. So if you go and plot this, it'll be nicely behaved away from 0, but close to 0 will wiggle faster and faster. So if you look close to 0, it looks like as you take x values that get close to 0, f of x gets close to all numbers in -1, 1. So it's like the limit wants to be everything in that range. That's impossible, so all that means is the limit x approaches 0 of this function f of x does not exist. So continuous functions definitely don't have that property given in theorem 3.8.13. So what we'll do next in the next video is we'll at least start in on the proofs of these. We might not make it through all of them, but I bet we'll make it through at least the first two before I decide I get tired. Nice. Well, I'll see you in the next one.